This is inclined planes, part 4. Part 4. I wrote it in red, so I'll underline it in black. In the last video, we had a situation where we had a ramp that was being raised up through a specific angle. Well, an unknown angle, actually. And we had a mass just sitting on the ramp. It was a 10 kilogram mass, and it was sitting there until the ramp got high enough, when angle theta became big enough, that it began to slide down the ramp. And the only other information we had was that the coefficient of friction was 0.2. Well, we drew our free body diagram, we put in the gravity, we said the friction was going up the ramp, trying to stop it from sliding, and we had the normal force this way, and of course we resolved our components of gravity, and we went through this entire process, and then we set up our net force equations, F net x and F net y, and over here we did F net y x, and we did all the work, and we discovered something. We discovered at the end that we came up with this equation that said tan theta equals 0.2, which implied that all you need to know is the coefficient of friction to figure out this tan theta. And we thought, is this a coincidence, or is this actually something that is happening? Maybe it's just the way the numbers worked out in this particular scenario. So what we're going to do is we're going to find out. We're going to find out if this is true for all numbers. And we're going to do that by drawing the same picture. We have an angle theta. This time, though, we'll just call our coefficient of friction mu, so it can be any number. And we'll call the mass of our object m, so it could be any number. And then we will repeat the process. We will draw in our force of gravity, Fg. And the best we can do for Fg at this point would be mg. We're not even going to use 9.8 for g, because we're using no numbers at all here. Even though we know g is constant, sometimes these numbers cancel out, so it's better to just leave it like that. Then we need a normal force, which we can do like this. And we said the frictional force would be pulling this way up the ramp. So we see we have the same picture, and we just have no numbers. Then we do the same thing we did before. We resolve the gravity into its vertical and horizontal components. Remember that we tilted our reference frame so that the x-axis is the slope and the y-axis is perpendicular. This angle, theta, we know is the same as the angle of the ramp because we've shown how that works, how the geometry shows that to be true before. So here we have mg and cos theta, and that's the best we can do for that, and that's our fgy, the y component. And over here we have our fgx component, which is mg sine theta. So without any numbers, we jump into our net force equations. Maybe I can do the F net y equation right over here. F net y, it still equals the normal force and the component of gravity, Fg, in the y direction. We said that the net force is going to equal 0 in this direction because there is no acceleration upwards or downwards of the block along the axis, the y-axis, no up and down motion. And so the force of the normal goes here, and then we have for Fgy, we have an mg cos theta, and because the arrow is pointing down, this has to be a number that's negative. We have to tell the math that that's a downward force. We bring it to the other side, mg cos theta equals Fn, or the normal. And that's all we can do for that. So then we move on to the F net x, which is, in this case, the two arrows that are horizontal, friction, and Fgx. So we write those in, force of friction and Fgx. Then we want to fill this out as much as possible. Just like in the previous video, the point where it just begins to slide is the point where the net force in the x direction is also 0. The friction is mu Fn, and again we have the Fgx component right here, mg sine theta, and it's a left arrow, so I'll tell the math that it's left with a negative sign, and I'll write mg sine theta, and of course we can then fill in what we have for the mu. Well, we just have a mu in this case. But we do know the normal force. We figured it out over here, so we can bring that down and substitute it into the equation mg cos theta, and we still have our minus mg sine theta. And I think you can almost taste the answer if we move the mg sine theta to the other side, changing its sign, equals mu times mg cos theta. The m and the g can be divided out of the equation, and if we divide by, well, let's do one step at a time. We'll take those out so you can see it. And if we divide both sides by cos theta, sine theta over cos theta equals mu, which means that tan theta equals mu. So this is actually true for all situations, but here is the big caution. Caution in red. This statement that tan theta equals mu, we have proven to be true, but only in this exact scenario or situation. You can't use this if anything in your problem is different. If there's an applied force that's added in the picture, if there's any change in this initial picture of any kind, it has to be this situation only. So it's a useful formula, but it's not super useful. It's not going to win you a Nobel Prize. But it is kind of handy to have in your back pocket. But if something else were to change, if there was an applied force or anything added on, pulling or pushing in any direction, then of course that would change the whole scenario. So this little cute expression only works in a scenario that's exactly like this one, where something is just beginning to slide as a ramp is being raised, and it's really only the gravity that's causing it to move, and it's a war between the gravity and the friction. And that's the end.